introduction. So I'm old school kernel hacker working at 1&1 Internet. It's a web hosting company, and I'm working at operations near the sysadmins. That's the reason why I'm here. And I want to talk about geo-redundancy, that's replication over long distances. Small agenda. We have an SLA of 99.98, almost 4 nines, measured end to end. I will explain some details about the environment where it's working, where I have developed Mars. And then I should focus in this talk just about the systemd interface, which is a new feature now. Simon and Ewan have told me that I should assume that you already know how Mars is working. If you have questions about it, ask afterwards, or I should give a small short intro. If you know DRBD, then you know Mars is very simple, very similar in the interface, but the internal engine is completely different. It works via transaction logging and is more similar to MySQL replication, asynchronous replication of MySQL than to DRBD. Okay, let's start. We have an SLA, which is end-to-end. It means include everything, including human error or long-distance outages of the network and whatever. And this means that the existing Mars installation there must be much better. I don't know it exactly because any outages of servers I notice, in most cases it's hardware, defective RAM or whatever. So it's for me it's clear that it's extremely reliable. So just a little bit about the background. Well, we are not as big as Google is, but we have a few data centers on 2 continents, and pair distances more than 50 kilometers, and a few millions of customer home directories and shared hosting here, a few billions of inodes in total to be backed up, and so on, a few petabytes of data and instances, and we have a data growth of about 20% per year. And this means it's a challenge for local storage, because we don't have network storage for good reason. But dealing with local storage is possible thanks to Mars, because Mars can also migrate data during runtime while it is being changed by your application. You can migrate it to a different host, and we have used it, for example, for lifecycle, for hardware lifecycle. And there's an open source project for dealing with this called Container Football. It's also on GitHub, like Mars. So now the main point of this talk here. What's about cluster management for long distances? Long distances are completely different from crossover cable in the same rack or in the same room of the data center, or short distances on the same campus. Long distances are a different model in distributed systems. And well, the first attempt would be theoretically, potentially, use your own proprietary cluster manager like here. Could use the mouse pointer probably, yes, here, this one. Our own one is not public, not usable for you. Of course, typical sysadmin would first try the existing cluster managers. So of course, will they work? Several teams in our company have tried and they have failed. It doesn't work as expected because of split brain. I think the reason is probably that the original model, as it has been, before it has been called pacemaker, the original heartbeat, is a distributed shared memory model. It's strict consistency originally, and it looks like that this could be the reason. This is just my guess. Okay, there's a theoretical explanation of the CAP theorem, not for this talk here, but if you want to discuss, of course we can do. I have a slide in the appendix there. And what this talk about is using systemd as a cluster manager. Well, there's a reason for using systemd, because it's already in use everywhere for startup of VMs or whatever. It's clear it's a standard tool now, and it runs as PID #1. So even if you aren't aware of it, you probably have it in almost any Linux distro. There has been some critics that it's monolithic. There's the code, I have looked into it, but in reality it's very flexible and extensible via unit files you can write yourself as an admin. So, and there's another advantage, it has path, so-called path watchers, so it can monitor any changes in the file system and trigger actions depending on that. And this is used here. Mars has already a communication, the so-called symlink tree is distributed throughout the whole cluster. If you change something in one node, the other nodes can notice it. It's propagation of the whole tree throughout the cluster. And this means you can misuse this feature of Mars, this internal feature, as a generic remote control. So this is used here at the primary side. You say just switch this, at the former secondary side, you switch it to primary. And the old primary is automatically noticed, no, you should not be primary anymore, you should go to secondary mode. And this is used here. Mars has already an internal macro processor, which is reused here. And for creating units, systemd units on the fly out of templates. And you will see it in the next slide here. This is an example. It looks a little bit strange, but it's an ordinary systemd template you probably know already. So the file name here in the first line, where you see the bash, has two things. The one is the add symbol. Add with the resource name is a substitution operator, dollar symbol in most other macro languages. And the caret symbol, and the first, the MNT name, this is a match operator. This matches against a real template name, which is provided later. So this variable is filled by the actual name and can be used inside of the template like any other macro name. In the first line you have the eval statement, and this is a call of the internal Mars macro processor. It just converts from the given MNT name, which is a convention of systemd. It doesn't contain slashes, but dashes. The dashes for instead of slashes, and this is just converted back to a mount path, to a path name, just as for the mount point. If you look, my pointer doesn't seem, it works here. Here this mount is just what you typically use for a mount. The def Mars resource name is mounted into the mount path and the resource name. This is the convention here, always use the same name. And in order to trigger this, here is an example of such a path which is monitored. So if you, in the /Mars system tree, you have the resource name here and a symlink which says which node should be the primary now. It should go primary. And if it's not the own machine name, the systemd at the former primary knows that it should go to secondary mode. That's the idea here. Because these symlinks are propagated automatically in background throughout the whole cluster, you can have a fully automated handover here. Okay, any questions for this? It's clear, hopefully. The current state is I have it not yet in production, and it has it's in beta version, because after releasing it, I have detected that system control is not re-entrant. If you call system control from within such a template, for example, you get a deadlock potentially, and it's only you need some stress testing in order to detect this. Most cases, 99.whatever%, it's okay. But in some cases it can deadlock, and therefore at the moment I use breakable locks for protection. But this is hopefully changed in future, so at least the parallelism between several resources is necessary. And I will do this in the next time. Okay. The usage is very easy and simple. This is why I call it easy. You write a template once and you install it. And if you create a resource dynamically during runtime, typically Mars rm create resource here resource name and what's the underlying disk to be used for replication. Then you create, for example, a file system, or you can flip this both. You can first create the file system and then create the mouse resource because the content is exactly the same, just replicate it. And the only new command you need to know here is the new mars rdm set systemd unit for the resource name. And now you provide two units, the start and the stop unit. They should be different than ordinary because the start unit typically is the top of the whole stack, and the stop unit is the bottom of it, just the unit using the def mars. Okay, so the idea is you give those two units, and the rest is done by the dependencies of systemd. Systemd will automatically check all the dependencies noticed inside and do some parallel work, of course, if it's possible by the dependencies, or sequentially, depending on what type of dependencies you have specified there. So if you are already a user of systemd, it's not new for you. So now what's happening at runtime, if you switch the primary, you say on some secondary host, you say, please become primary, resource name, and that's all. The rest is now handled automatically. The old primary does the equivalent of system control stop of the stop unit name you have provided once. It's set up here. And this step is new. The old primary goes to secondary mode. This is already in Mars for years now. New primary becomes primary, also in Mars for years. And the last step is that the system control, the same unit, is started on the same but on a different host. So you have a full handover of all your status, of all your state, of all your data to a different machine. And in ideal case, you should have some BGP or whatever in the network so that your new site is recognized under the same IP as before. That's a typical setup for this use case here. So you have location transparency with respect to your resources or with respect to your applications running inside of your machines. And this is the planned handover. The unplanned handover, it's a little bit shorter. You have to use, similar to DRBD, you're disconnecting first, and then you say primary minus foss. That's all. That's the main difference. So, Mars current status. If you already use Mars, you know the GitHub repo where it is. In the meantime, I have split the documentation into two parts. The one is for sysadmins. So, sorry, it was wrong. The user manual is for sysadmins, for people who already want to use Mars. It has step-by-step instruction if you are new to Mars, and how to compile the kernel module yourself, and so on. And what's more tailored for if you want to know whether Mars is for you, check the architecture guide. I have, my boss has told me I should address managers' need also. So I have several colored boxes now in the new version of this guide, addressing the needs of manager about cost and several other things about reliability. I have a mathematical proof, for example, that the sharding architecture used at 1&1 is the most reliable architecture at architectural level, and it's much better than any big cluster. And there's mathematical proof why this is the case. Please check it if you are interested in this. Okay, then the other, if you already use Mars, you know it, that it's productive since 2014. It's the backbone of our company, Geo-redundancy feature. At the moment, it doesn't scale very well in the number of resources. The maximum in production is 14 at the moment because we have fat LXC containers, not micro containers. So the old hardware IBM blades have been moved into one LXC container each. But typical density is now about 7 to 10 containers per hardware. In one pizza box, we have around these 10 containers. And thanks to this density, the TCO has halved. I cannot tell you the exact numbers, but if you are a manager and read this, you should check this. Okay, no, the real last slide is this one, what I'm currently working on. First thing is what sysadmins already using Mars will hopefully like. It's new checksumming. I did some, the traditional Mars is using MD5 checksums in the transaction log file, and it has rescued our life several times. For example, if your BBU cache is damaged in your hardware RAID controller, you get disasters you cannot imagine, and typically the secondary side won't replicate this because of these checksums. So it can save your life having these checksums. And recently I checked whether there are several other checksumming operations in the kernel. Checksumming function at CRC32C is already used in the network stack, and it's faster by about a factor of 10 or even more than 10. So I think this should be good for CPU consumption, and it's called in the callback path. Other Linux drivers are using interrupt context here, and in the callback path doing some MD5 checksums is a very expensive operation. So log file compression is also implemented in this new version, which is almost ready for release, but not released at the moment. And I've checked that zeblib is unfortunately very expensive, while LZO is obviously, if you know it, is very light, consumes not much CPU. And independently from log file content compression, you can compress the network transport now as the next new feature. So then what's to be done in future? Metadata scalability here. The number of resources should be pimped. The I/O data paths are already scaling very well, and one of the next tasks is more hosts per cluster. And Linux kernel upstream is something I will talk about tomorrow. Tomorrow there's a talk at the kernel miniconf by me, but from a different perspective for kernel hackers. So that's it. I think I'm in time. Is it correct? 5 minutes left. Yes, that was intended, because I want to have a vivid discussion now, if it's possible. So if there are questions, it's moderated by Simon. Yes?
Hello. Hi, my name is Alex. Just a quick question. How do you implement fencing if you only have 2 data centers per region? Or like, how do you prevent split brain?
How to prevent split brain is the question.
Yes, because you only have in one region.
Yes, ordinarily you have a handover, and the handover ensures that you have strict consistency inside of each version, of course, because this is the semantics of a local block device. And by handover, it's also strict consistency over the network. It takes a few seconds until all the data has been transferred and is checked by checksums. Also metadata checksums, the so-called version links in the symlink tree, and they ensure that I know whether split brain has occurred or not. It's a passive detector, and the switch over, the handover logic is checking this. So in certain cases, when the network is very congested or you have other problems, it may happen that during handover attempt you get an accidental split brain. That can happen, but you will see it, at least at the new primary side. Okay, this is the answer to the question already? We can talk later. Yeah, we can talk later. Just talk with me. So you are right, this is the consistency model. You have 2 different consistency models at the same time. At the local node, you always have strict consistency. In the distributed system, you have eventually consistent. But in case of planned handover, it's waited until the eventually consistent is really consistent, strict then. Okay? So this is not a problem. It just may take a longer time in case the network has a problem, of course. And the model is completely asynchronous. In Mars, the communication model is any message can take an arbitrary time. So in theory, you could replicate to planet Mars, in theory. Yes, but the TCP protocol won't do that in practice. But the model employed is in this direction. So, okay.
Any other questions?
And there's some old presentations from me about this. Just check it out.
Oh, one last question.
Okay.
So how long can the connection be down for and it still retain consistency? So if the connection between the two data centers is down, wouldn't you, because it's asynchronous, wouldn't you end up DOSing yourself trying to create the consistency?
I'm not sure if I understand your question right, but the model of Mars is connections are transparent. So if you have a certain setup, it always tries to reconnect in background. And connections can even be in parallel, the so-called socket bundling feature. If you have a transfer from primary to secondary, they are typically configured by default 2 connections in parallel in order to overcome network bottlenecks, like packet loss and so on. And this means if you lose connection, you have a network outage, like CAP theorem says, you have a separate network outage. Of course, no data can be transferred anymore, but the network is recovering, or has recovered. It automatically reconnects, and this is a difference to DRBD. If you are coming from DRBD, you have to issue command DRBD connect. This is not necessary with Mars. It's connecting automatically.
So
okay.
say you had a whole heap of data that needed to be moved back over. Is there a maximum amount of data that needs to be moved over to the secondary?
Yes, of course you can, in case of a network outage, you have 2 options in general. You can just wait until it's gone. Probably the most important option in practice, if you have the network outage where the primary is reachable for your customer traffic. Then you shouldn't switch over, hand over. Otherwise, you can fail over, and of course, then you get a split brain. It is detected. This means you need a fast full sync. The fast full sync is a little bit different from DRBD. In DRBD, you have these bitmaps, which are recording the deltas, the changes in the block device. Mars does a fast full sync, which is similar to MD5 checksumming, to rsync. Both sides, it also transfers only the changes, but on the disk, all data is read again. Okay, this is the main difference to the RBD. It's a little bit more expensive with respect to disk I/O, but on the network, similar things happen. So it answered your question. Yeah. Thank you. So I think time is over or not? Yeah. Oh, okay, it's your moderation. Thank you.